Here we have the cosmological history of the Hubble constant in the primordial universe. This illustration contains 3 graphs. It is important to note that all required equations appear on the illustration, so everything you need to replicate this solution is right in front of you. Everything you see here has been forwardly derived from first principles and nothing has been doctored, modified or fine-tuned. The first graph is the magnitude of the Hubble constant. The second graph is the rate of change of the Hubble constant in the time domain. The third graph depicts cosmological inflation and expansion. The next important feature to recognize is that each graph contains regions. Each region defines a specific phase of the evolutionary process. Region A denotes the period we term Planck inflation. This runs from t equals 0 to t alpha, which is the instant of the Big Bang. The cosmic microwave background radiation was 0 Kelvin at the instant of the Big Bang. So, the Big Bang was in fact cold, but thermally inflated extremely quickly. Region B denotes the period we term thermal inflation. This runs from T alpha to T1. At T1, the cosmic microwave background radiation reached its maximum value, which was approximately 10 to the 31 Kelvin. Region C denotes the period we term Hubble inflation. This runs from T1 to T2. From the graph, you can see that the Hubble constant reduced to 0 by T1 for an instant, but immediately shot upwards again to its maximum post-T1 value, at T2. Its value at T2 was approximately 10 to the 60 km per second per megaparsec. Region D denotes the period we term Hubble expansion. This runs from T2 to the present epoch. Region E denotes the period of cosmological inflation, from t equals 0 to 2t phi rho. So, cosmological inflation ended when the universe was approximately 10 to the minus 23 seconds old. Region F denotes the broader period of cosmological expansion, from the Big Bang at T alpha, to the present epoch. An important takeaway from this illustration is that cosmological inflation was a multi-event, multi-process period. This is why we term it as being the cosmic envelope. Let's now look at the behavior of the cosmic microwave background radiation. Here we have the cosmological history of the cosmic microwave background radiation in the primordial universe. You will instantly recognize the black body radiation curve similarity. This was not intentional. Black body equations were never utilized in its derivation, but the fact that its shape mimics a black body curve is very comforting. The illustration contains 4 graphs. The first graph is the cosmic microwave background radiation in the time domain. Note that the temperature of the universe at the instant of the Big Bang was 0 Kelvin, so, the Big Bang was cold. The cold Big Bang model was abandoned by physicists after the WMAP and Planck satellites observed the cosmic microwave background radiation which we see today. However, in our solution, the cold Big Bang hides behind a hot Big Bang observation. In other words, the universe was 0 Kelvin at the instant of the Big Bang, but rose to 10 to the 31 Kelvin within the first 10 to the minus 42 seconds, so in fact, the WMAP and Planck satellites are blind to cold Big Bang evidence. Hence, cold Big Bang models cannot be excluded from the standard model of cosmology. This is an important takeaway. The other graphs are the first time derivative, second time derivative, and third time derivative.